Greetings. This is information for Unit 5, and for this unit I have a couple examples to go over. The first example comes from the same data set that we looked at in our previous unit, which is looking at the relationship between attributions and feelings of anger in married couples. If you recall, attributions are thoughts that people have that are explanations for another person's behavior. So in a couple, if something negative happens and one person thinks, well, I think my partner's to blame for this, or I think my partner acted on purpose, I think my partner was being selfish, those would be all attributions, and specifically negative attributions. And the idea is that when people make negative attributions, they're likely to feel angry. And we also have another idea here that maybe, at least to some small extent, women might be more event dependent and men might be more schematic. That is, when women feel angry, maybe their anger is especially closely associated with their thoughts, what's going on here and now in the relationship, in the moment. They're attentive to the details of what's going on in interpersonal interaction, and when they feel angry, it's because they're attending to those details of what's going on in that particular interaction. In contrast, maybe to some extent, men might have a tendency to have their anger more dependent upon their global appraisals about the relationship as a whole, so that they're thinking, well, am I generally happy in my relationship, or am I generally unhappy? Do I think my partner generally does stuff that I blame my partner for, or is my partner generally not to blame for things? And that maybe men's anger is more closely associated with their global appraisals and maybe not quite as closely associated with their event-dependent appraisals about events in their relationship. So what do we have here? We have the same data set we looked at in our previous unit. We have 77 couples. Each couple came into a research lab on a couple occasions, and they engaged in 4 problem-solving conversations. For each conversation, they identified an area of conflict in their relationship. Then each partner went to separate rooms and they completed assessments, completed several questionnaires about that conflict and about their relationship. And then they came back together and they engaged in a problem-solving conversation where they tried to resolve that conflict. And all of our data for this example come from those questionnaires they completed prior to a conversation. And actually, we're just going to look at just a single conversation, which is the very first one they had, or conversation number 1. So this will be a little bit different than our previous example. In our previous unit, we were looking at changes across 2 different time points, across 2 different conversations. We're not going to consider that type of change here. We're just going to look at variables that were all collected on the very first assessment occasion. And this example, we're going to have 4 variables. 2 of the variables we'll call event-dependent. I have event-dependent pre-conversation questionnaire. That's the questions they completed about their upcoming conversation, their problem-solving conversation about an area of conflict. They completed these before that conflict, so we call them pre-conversation questionnaire questions. And these are the first 2 here that I have to show you are event-dependent assessments, in that they're asking questions about that particular conversation, about that particular event they're about to discuss. And actually, these are the same 2 variables we saw in our previous unit. One is an event-dependent measure of attributions. So in this conflict, you're just identified, you're about to talk about it with your partner. Do you blame your partner for it? Do you think your partner acted selfishly? We had 6 questions. And the alpha reliability, we had good reliability, 0.8. And I'm going to name this in our data set just ATT1, which stands for attributions in the first conversations, or attributions about this first conflict they're about to discuss. And then we also assessed how angry they felt. 4-item scale, measuring what angry feelings, or sometimes I call these hard emotion feelings, the extent to which they felt angry and annoyed and irritated with their partner. 4 questions, had good reliability, and I'm going to name this hard 1, stands for hard emotion in the first conversation. And again, both of these are just pertaining to their time 1, or their very first assessment session scores, and we're not using scores from the other conversations, and we're not doing the change scores like we did in our previous unit. So we've got 2 event-dependent variables, And then we also have two schematic variables. And these are going to be questions asking about the relationship as a whole. We assess these single assessment on a single occasion. We asked about overall what are the types of attributions you make, and we're going to call that trait attributions. So we've got two different types of attributions. We have event-dependent attributions, where we asked about attributions in a particular context, about the conflict they were about to discuss. And now we have trait attributions, where we want to know, well, what are the types of attributions you typically make for your partner when something negative happens in your relationship? And we'll call that your trait attributions. To assess this, we gave people some scenarios. We had 4 different scenarios. These were common negative things that might happen in a relationship, such as, say you're talking and your partner doesn't seem to listen to what you're saying, or say your partner criticizes something about you. So in those scenarios, if that happened, what types of attributions would you typically make? And we asked people to rate 3 different types of attributions, such as, would you blame your partner for this? Would you think your partner acted selfishly? And so they did 4 scenarios. Each scenario got 3 ratings of 3 different types of attributions. And then we summed all that together to get a total trait attribution score that had a good reliability. Alpha was 0.87. And then finally, we assessed satisfaction. How happy and satisfied are you in your relationship? So this would be another schematic measure, getting someone's global overall appraisal of the relationship. And we used a scale that actually was widely used many years ago. It's not used quite so much now, but a measure called the Dyadic Adjustment Scale, or DAS for short. Dyadic Adjustment Scale, just a measure of satisfaction. So it's measuring schematic variable globally. Overall, how happy and satisfied do you feel in your relationship? There were 7 items, at least the version we used had 7 items on it, and the reliability was adequate, 0.79. So we've got 2 event-dependent variables, event-dependent attributions, event-dependent anger, 2 schematic variables, schematic attributions or trait attributions, and relationship satisfaction. In this analysis, the anger will be the outcome variable, and the predictors will be event-dependent attributions, trait attributions, and relationship satisfaction. And the basic idea that we want to look at here, or one hypothesis we might have, is that maybe what we would find is that for women, the best predictor of their anger will be the event-dependent attributions. Whereas for men, maybe the schematic variables will be a better predictor of their anger. That for men, their anger would be best predicted by the trait attributions and relationship satisfaction. So let's take a look at the results and see what we have. So first, here are the results for wives. So we have 4 variables. Hard 1, that is our outcome variable, or we might call that Y. DAS, that's the schematic relationship satisfaction variable. I'm going to call that X1. And here we have ATTRIBS, that's the schematic attribution variable. We'll call it X2. So we have schematic relationship satisfaction, then schematic attributions, and then finally ATT1, we'll call that X3. And that is the event-dependent attribution variable. So we've got those 3 predictors, 1 outcome. We have the means and standard deviations for each. And then down at the bottom here, we have correlations. And recall that with multiple regression, we have 3 types of questions we can answer. We can look at the question of what are the effects of X on Y, ignoring the other variables in the equation. What are the effects after controlling for the other variables in the equation? And what are the effects of all the predictors taken together in predicting Y? So the correlations will address that first question, what are the effects of each predictor in predicting the outcome variable Y, or what's the association between each predictor and the outcome, ignoring the other variables? So here we have the correlation between the Dyadic Adjustment Scale and heart emotion. And heart emotion is our outcome variable, or feelings of anger. That correlation is negative 0.115. It's a very small correlation. And if we look down here at our p-value is 0.161. That is not significant. It is not less than 0.05, and so we cannot reject the null hypothesis here. We do not have a significant correlation between relationship satisfaction and anger, at least for wives. Next we have ATTRIBS. That's the schematic trait attribution variable. The correlation here, 0.208, that's the correlation between trait attributions and anger. And that's a small correlation, but it is significant. The p-value is less than 0.05, not a whole lot less than 0.05, but it's less, so that qualifies. So that is significant, and we can say we have a relationship between trait attributions and heart emotion for wives. And then finally, at the bottom here is our ATT1. That is the event-specific attributions I made for this first conversation. And the correlation is 0.343, so that's a moderate-sized correlation, and that is definitely significant. Our p-value is 0.001, so we'd only get an effect that big once in 1,000 times if the null hypothesis were true, so we can definitely reject the null hypothesis and claim we have an effect here. So that's the results looking at the effects of each variable, ignoring the others. Let's go on down our output to the next page of output here for wives. Why don't I start at the very bottom here where we have our output for the regression equation. Now in our previous unit when we had simple regression, we just had one constant or the intercept and one slope. And now here we have a constant and several slopes. We have one slope for every predictor variable. So 2.28, that's our intercept. 0.06, that's the slope for the dyadic adjustment scale, DAS, or relationship satisfaction. 0.09, that's the slope for trait attributions. And 0.38, that's the slope for event-dependent attributions. So that 0.38, for example, that tells you if event-dependent attributions go up by 1 unit, we expect wives' anger to go up by 0.38 units. And 2.28, that's our constant, or that's our intercept, and that's the expected value for y when all the x's are held constant at 0. So those are our, that column, that's our unstandardized beta weights. If we go over here, we have our standardized betas, which tell us if x goes up by 1 standard deviation, how many standard deviations does y go up? And standardized betas are easier to interpret because they all have the same scale. We can know what they mean. And the scale is also analogous to a correlation, so we can get a sense of what's a small, medium, or large effect. And we see, again, we have a medium effect here for event-dependent attributions, 0.32, and the effects for the first two variables, the schematic variables, satisfaction and trait attributions, 0.03, 0.06. Those are very small betas. Are they significant? Well, we can look at our t-values over here, and the t-value for a unstandardized beta is the same as the t-value for a standardized beta, because both betas, standardized or unstandardized, it's looking at the same question of what's the effect of this variable, controlling for all the other variables in the equation. So regardless of how you do it, you get the same t-value. And so we take, for example, our beta divided by the standard error of beta to get our t-value over here. And then on the last column, we have the p-value, or the significance. And we can see that the beta for a dyadic adjustment scale, DAS, that is not less than 0.05, so that is not significant. Our p-value for trait attributions is also not significant. That is not less than 0.05. So in this case, we had a significant correlation. When we were ignoring the other predictors, there was a significant association between trait attributions and wives' anger. It was a small correlation, but it was significant. Now, when I put the other predictors in the equation, and after we're controlling for the effects of the other predictors, we see that the trait attributions does not explain any unique variance above and beyond the other predictors in the equation. That becomes non-significant. But important for our hypothesis, this is actually what we expected for wives, in that we do have a significant beta weight for their event-dependent attributions. The p-value is 0.014, and that is significant. That is less than 0.05. So we can say this beta weight, for example, a standardized beta weight 0.32, that is significant. That after controlling for the other variables, we still have a significant association between the extent to which wives make negative attributions, event-specific attributions, and their feelings of anger. So what about husbands? Let's take a look at their output and see what we have here. So first, we'll look at their correlations. The outcome variable is heart emotion. Correlation between DAS, relationship satisfaction, and heart emotion is a large correlation, negative 0.578. It's negative. That's important because it means that as their satisfaction goes up, their anger goes down, or if satisfaction goes down, anger goes up, which makes sense that it would be that way. So it's a negative correlation. It's actually a large correlation, 0.578, and it is significant. Our p-value, it rounds to 0. We don't know exactly what it is. It's 0.000 something. So very tiny p-value. So this is definitely significant. That p-value is less than 0.05. So we have a significant effect and a large effect for husbands. Which note that was different from wives. For wives, that effect was actually non-significant. For husbands, this is actually a large effect and significant. For husbands' trait attributions, the correlation is 0.385. Moderate size correlation, but that is also significant. P is less than 0.05. It's 0.000 something. So that's significant as well. And then finally, for event-dependent attributions, ATT1, that correlation is 0.266, and that is significant. So for husbands, all three of these were significant. The biggest effect was for relationship satisfaction, for DAS, Dyadic Adjustment Scale, or relationship satisfaction. So we got the biggest correlation there. But it turned out for husbands, all three of these were significant. At least they were significant when we ignore the effects of the other predictors. Each variable by itself, ignoring the effects of the other predictors, had a significant correlation. Let's go on and see, do these effects remain significant after controlling for the other variables in the equation? If we put things into a regression equation and get the effect of each variable controlling for the others, what do we have here? So let's look down to the bottom where we have our beta weights. Standardized beta weight for relationship satisfaction, that's still a very large beta weight, negative 0.53, and that is still significant. But these other two, for trait attributions and event-dependent attributions, both attribution variables, those beta weights get smaller, and look over here where it says significance, those p-values are not less than 0.05. Those become non-significant. So for husbands, when we put everything together in the same equation, relationship satisfaction is still a predictor of their anger. That relationship satisfaction explains unique variance of their anger after controlling for all the other variables in the equation. But the two attribution variables, both trait attributions and event-dependent attributions, became non-significant after controlling for satisfaction. So that's a little bit different. We were expecting that both schematic variables might be significant for husbands, and it turned out that only one was significant, at least after controlling for the other variables in the equation. Although I suppose it's consistent to the extent that for husbands, we still have a pattern where the best predictor of husbands' anger was their satisfaction, which is a schematic variable, and the best predictor of the wives' anger was their event-dependent attributions, which is an event-dependent variable. So I guess on the whole, we're consistent with the general hypothesis that we have for this study. Then up at the top, we have that the data that will address our third question, which is what are the effects of all three predictors taken together? And here's our R squared multiple correlation, and that R squared is 0.356. So we're explaining, if you round to 0.35 or 36, we're explaining about 36% of the variance in husband's anger. These three predictors taken together explain about 36% of the variance in husband's anger. And is that R squared significant? We test the significance of our multiple correlations squared with an F test from the ANOVA table. And so our F is 13.24, and that is significant. The probability of getting an F that big, if the null hypothesis were true, is something less than once in 1,000. We don't know exactly what it is. It rounds to 0.000, but we can just say P is less than 0.001, something less than once in 1,000. Okay, so what are some of the things that I might ask you to do with this output? Let's continue on with a husband's output here and look at the types of questions that I might ask you on a test or in homework. So one question is this: what is a typical distance scores deviated from the mean of y? Well, hopefully when you read that, you think, oh, I have seen this question many times before. This is becoming a very familiar question. That is asking me for a standard deviation. And given that we're looking at how far scores deviate from the mean of y, that's asking you for the standard deviation of the y variable. So the only thing you need to do here is to identify which variable is x and which were the x's and which are the y's. And we know that the hard emotion, hard one, that is our y variable, that's our outcome. Our standard deviation, 1.33, so the answer to that question is 1.33. Next question says, compute the t-statistic for the correlation between x1 and y. This is the same thing we did in the previous unit, and I'm asking you to redo it again here. And it's the same thing as before, where we have here's the correlation between x1 and y. If we just number them, DAS would be our first x variable, so we'll call that x1. And the correlation is negative 0.578. And what is the t value for that correlation? And as we did before, that we have to deal with the fact that the output does not give us the standard error and it does not give us a t value, so you will need to calculate that yourself. And so we can plug in our formula. First, we need to calculate the standard error of our correlation, where we take 1 minus the correlation squared divided by n minus 2. And if you plug all that in, you should get a standard error of 0.09486. And now we can take our correlation, 0.578, our correlation of 0.578, divided by the standard error of our correlation, standard error 0.09486, and we get our t value, which is negative 6.093. So that is the t-statistic. That answers the question. Compute the t-statistic. We got a t value of negative 6.093. What else? I can say, what is the typical distance that observed scores deviated from their predicted values? So what am I asking for there? How far observed scores typically deviate from predicted values? Well, that is the standard error of estimate. And that's pretty easy because right up here is given to us the standard error of estimate is 1.09. So that is the answer to that one. Or I can make things tricky and I could say, if I just give you just this ANOVA table and nothing else, then how would you answer that question? It's still fairly easy because you know if you take your error, your mean squared error or your mean squared residual and take the square root, you will have the standard error of estimate. So take 1.19, take the square root of that, and you will get the standard error of estimate, 1.09. Let's see, what else? What is a percent of variance that's been explained? Well, the R squared tells you the percent of variance that's been explained. 0.356, that's our R squared. And how would you get that if I just gave you the ANOVA table and nothing else? We've done that before. You take your explained variance sums of squares, in this case 47.16, divided by your total variance sums of squares, 132.61, and you would get the percent of variance explained. And what is the correlation between observed scores and their predicted values? So what statistic gives you the correlation between observed scores and predicted values? That is your multiple correlation, the capital letter R. So right up here, capital letter R, 0.596, that's a multiple correlation. And one way of understanding what a multiple correlation is that it's the correlation you would get if you calculated everyone's observed score on Y and got everyone's predicted score on Y, and then calculated the correlation between the observed and predicted scores. That would give you the multiple correlation, the capital letter R, which is also the exact same thing as if you calculate R squared and then take the square root, you will have a capital letter R. And both capital letter R, the multiple correlation, and R squared, neither one of those can take on negative values. Those will always be positive values. And so our capital R multiple correlation is 0.596. And of course, you could get that from a ANOVA table. If you first calculated your R square and then take the square root, you would have your multiple correlation. What else? We have, after controlling for the effects of other predictors, how many units is y expected to increase when x1 increases by 1 unit? Well, what tells you that? That's what the beta weight tells you. The beta weight tells you how much is y expected to increase when x goes up by 1 unit. So if I'm asking about x1 here, the beta weight for x1 is negative 1.14. That is for husbands. If their relationship satisfaction, if relationship satisfaction goes up by 1 unit, we expect their anger to go up by negative 1.14 units. In other words, if satisfaction goes up by 1 unit, their anger is expected to decrease 1.14 units. Then the next question is very similar. I just changed one word. So the question we just looked at said how many units is y expected to increase when x1 increases by 1 unit. And then now I'm going to say, after controlling for the effects of the other predictors, how many standard deviations is y expected to increase when x1 increases by 1 standard deviation. So it's the same question, but rather than talking about generic units, I'm now talking about standard deviation units. So if x1 goes up by 1 standard deviation, how many standard deviations should y go up? What tells you that? Well, that is the standardized beta. And the standardized beta for x1 is negative 0.53. Because the standardized beta is the beta you get when everything is turned to z-scores prior to analysis. And when you turn everything to z-scores, the units become standard deviations. So 1 unit is 1 standard deviation. And so that negative 0.53 tells you if the dyadic adjustment scale, if the satisfaction goes up by 1 standard deviation, anger should go down by about a half a standard deviation. Let's see. Here I have a question where I want you to fill in the blanks. I have a sentence here and want you to fill in the blanks so that we make an accurate statement. And it's similar to the previous questions in that it's wanting you to show that you understand what a beta weight means and what it's telling you. So, and this page here is looking at an explanation of the beta weight for x1. It says, y is expected to increase by blank units if x1 increases by blank units, and x2 is blank, and x3 is blank. So how would we fill that in? Well, y is expected to increase by negative 1.14 units if x1 increases by 1 unit, and x2 is 0, and x3 is 0. And so this is just asking you to show that you understand what a beta weight means. So the beta weight here for x1 of negative 1.14 says that that's how much you expect y to increase if x1 increases by 1 unit and all the other predictors are held constant at 0. And we could do a similar type of question. We could do this for like x2 or x3. We could say that, for example, for x2, y is expected to increase by 0.29 units if x1 is 0, and x2 increases by 1 unit, and x3 is 0. So we could do a similar type of questions for all of our predictive variables. Another thing we could do with this data set is I could say, I could give you the output here, but I could scribble out the t-values over here and say, you tell me what a t-value is. So for example, for x1, I could say calculate the t-value for x1. And so for that, x1 for data, we take our beta negative 1.14 divided by our standard error, which a t-value is always a statistic divided by its standard error. So 1.14 in our numerator divided by our standard error, which is 0.24, and I get negative 4.75. Which, by the way, that's a little bit off from what it shows in the table up here. That the SPSS output says negative 4.65, and that's just because when we're calculating it here, we're dealing with our beta and our standard error are rounded. And if they were carried it out so they weren't rounded, then we would get exactly what was on the output here. And of course, if you were doing this on a test or on homework, I would assume that negative 4.75 is a correct answer, because that's what the number you get if you calculate things given the numbers you have to work with. Let's see, what else? We could calculate the partial correlation between x1 and y. And to do that, we can use our formula, kind of a shortcut formula, for calculating a partial correlation, which is the square root of t squared divided by square root of t squared divided by t squared plus degrees of freedom. So our t for this beta, for beta 1, is 4.65, so I plug that in here. And this t squared divided by t squared plus our degrees of freedom. And in this case, we have 72 degrees of freedom. And you can calculate that as degrees of freedom are going to be our sample size minus the number of predictors minus 1, which is our error degrees of freedom. And at the bottom here, I've kind of zoomed in on this piece of our ANOVA table that shows we have 75 total degrees of freedom, that's n minus 1. Our degrees of freedom for explained variance is 3. We have 3 predictors. And our degrees of freedom error is 72. 75 minus 3 gives us 72. So we have 72 degrees of freedom, and plug it in right there. And that gives us a partial correlation of 0.48. But before I say that's our answer, I want to make note of one thing, is that when we use this formula, we cannot get a negative number. This is a shortcut formula that will help us calculate a correlation quickly. But one disadvantage of this formula is that it does not give us a negative value. And so what we need to do is to look up at our beta weights and say, well, is it supposed to be negative? In this case, we have, and you could look at the standardized beta or the raw score unstandardized beta. Either way, if those betas are positive, then we should have a positive correlation. But if they're negative, then we should have a negative correlation. So because our betas are negative, we know this is a negative relationship. That is, as satisfaction goes up, anger goes down. So we need to put a negative sign in front of that. When you report the actual partial correlation, you would need to put a negative sign and say our partial correlation is negative 0.48, because the relationship between those variables is negative. Okay, that's how to do a partial correlation. Now, we've looked at several things, different types of questions that I might ask you on a test or on a homework. Now, at this point, I want to take a step back a bit and look at what I sometimes call the 5 pieces of information. These are 5 pieces of information about an effect size, and an inferential statistic. And that is situations where I might give you a question and want you to answer the question by telling me 5 things. First thing to tell me is, what is the name of a descriptive statistic that gives an effect size that will answer this question? Number 2, what is the value of that effect size? Number 3, what is the name of an inferential statistic that can be used to test the significance of our effect size? Number 4, what is the value for that inferential statistic? And then finally, number 5, what is the p-value? What is the probability of that inferential statistic if the null hypothesis were true? So those are the 5 pieces of information. And with multiple regression, there are 3 types of questions that you can answer by giving me those 5 pieces of information. And those are the 3 questions we address with multiple regression. That is, what are the effects of a variable on an outcome ignoring the other predictors? What are the effects of a variable on an outcome after controlling for the other predictors? And what are the effects of all the variables taken together? If I have 3 predictors, what are the effects of all 3 predictors in explaining variance in a target outcome variable? So let's look at how you would address questions of effect size and the inferential statistic. That is, how you would give me those 5 pieces of information when addressing those 3 questions we can address with multiple regression. So first, we have, what is the standardized association between x1 and y without controlling for the other variables. So what is the descriptive statistic that gives an effect size that will answer that question? Well, that is a correlation. The lowercase r, the simple bivariate correlation. And we have the correlations in our output right on this page right here. And so, for example, if I'm looking at the relationship between x1 and y, that correlation is this negative 0.578 that we looked at a little while ago. That is a correlation between x1 and y that gives the standardized association between x1 and y without controlling for the other variables. Then, what is the inferential statistic that we use to test the significance of that correlation? Well, we use a t-test, so a t-value. The name of the inferential statistic is t. And we saw before our t-value, we calculated that to be negative 6.093. That's the t-value. And then finally, what is the p-value? What is the probability of that t-value if the null hypothesis were true? And that is printed already in our output. That's this significance right here, 0.000. We don't know exactly what it is. It rounds to 0.000. And on homeworks or tests, I would typically ask you to give me the p-value exactly as it's printed in the output. So if I ask for the p-value exactly as it's printed, you would type period 000, because that's what we see right here. Even though we know technically it's not exactly 0, it just rounds to 0 because it's such a small value. Okay, next question. What is the standardized association between x1 and y after controlling for the other variables in the equation? So, what is the name of a descriptive statistic that will give us an effect size that will address that question, that will tell us about the relationship between x1 and y after controlling for the other variables in the equation? Well, the statistic I'm looking for here is your standardized beta weight. And the standardized beta weight for x1 is negative 0.53. So that would be the answer for our effect size. Standardized beta is equal to negative 0.53. Do note that technically our unstandardized beta is also an effect size. Typically, if you're not familiar with the variables and the scale, then it's a hard effect size to interpret to know what it really means. And so for that reason, I'm not going to typically ask you to report that one. So as a default, if I'm wanting to get what is the best one to report for an effect size, I'm going to look for the standardized beta. And also that's specifically what I say up here. I say, what is the standardized association? So the unstandardized beta would have been the wrong answer to begin with because that is unstandardized, and I specifically asked for the standardized association. Now, one thing that you technically, if you wanted to, you could calculate a partial correlation, and technically that would also be giving you a standardized association between x1 and y, controlling for the other variables. But if you do that, I'm going to count you wrong because, well, I'm just not looking for that one, and what I want you to report is the standardized beta. Although both standardized beta and partial correlation are actually technically standardized effect sizes, the standardized beta is a little more common one to report, and it's also an easier one to report because it's given on the page, and if you don't have to calculate anything for that, whereas the partial correlation you would have to calculate that, and that's not given in the output automatically. So both to go along with what's typically done and to make things easier for you, as a default in this class, whenever I asked for the standardized association between x1 and y after controlling for other variables, what I want is the standardized beta. So in this case, for x1, it's negative 0.53. Then, how do you test the significance of that? What is the inferential statistic that we use to test the significance of our standardized beta? Well, the answer there is the t-test, or the t-value. So t is the name of our inferential statistic. And note that we used a t-test to test the significance of our correlation, and then we're going to use it again to test the significance of our beta. So both the correlation and the beta are tested with a t-test, although those are two different tests. With the correlation, it is a t-test for the correlation, where I take the correlation divided by the standard error of the correlation. For the beta weight, it's a t-test for the beta weight, where we take the beta weight divided by the standard error of the beta weight. So they're going to give us two different values, One will be the significance of our correlation, the other will be for our beta weight. And also keep in mind that the significance for a standardized beta and the t-value for a standardized beta is identical to a t-value for a unstandardized beta. And by convention, it's common to calculate the t based on the unstandardized beta, and then just note that that would also apply to a standardized beta as well. So we'll do that here. We can take our beta, negative 1.14, divided by the standard error of the beta. Our t-value is negative 4.65. And so our t-value for our standardized beta is also negative 4.65. That is our t-value. And then finally, what is a probability? What's the probability of getting a t-value that large of negative 4.65, or that extreme, if the null hypothesis were true? Well, this example has a lot of significant effects with very small p-values that round to 0. Because again, we have a p-value that rounds to 0, 0.000 something, or we could say less than 0.001, although on a homework or a test, I will say, give me the p-value exactly as it's printed. And so in that situation, type period 000 would be our p-value again here as well. And then our third question is, what is the total percent of variance in y explained by all three predictors taken together? What is the name of the effect size? What is the descriptive statistic that gives you an effect size that answers the question, that tells you the total percent of variance explained by all the predictors taken together? Well, that effect size is your r squared. And note that I'm asking about the total percent of variance explained, and the multiple correlation also is an effect size that answers the question about the effects of all predictors taken together. But it can't be, we don't call that the percent of variance explained. So if I specifically say percent of variance explained, then I'm looking for the squared multiple correlation, capital R squared. And that will be the default whenever I ask this question. That's what I will be looking for in this class. And that also follows tradition of typically when people report this effect size, typically when people report the effects of all the predictors taken together, what they report is the squared correlation and not the unsquared correlation. So the answer there, the statistic is capital R squared, our multiple correlation squared, and our value of that statistic is 0.356. Then, what is the inferential statistic that we use to test the significance of our multiple correlation squared? Or the multiple correlation would be the same thing either way. Well, that statistic is our F test, our F value. So the name of the statistic is F, that we get from our ANOVA table, and the value is 13.24. And then the p-value, the probability of getting an F that big if the null hypothesis were true, is, once again, rounding to 0.000, 0.00 something, less than once in 1,000. We know that much. And again, if I ask you for this on a test or a homework and I say, give it to me exactly as printed, you would simply type period 000. So that is how we would address those three questions. Now let's look at how you would give me written summaries of results. And we've been going over output for husbands. Let's switch back to wives and look at their output and address the issue of how would you give me a written summary of, say if we got this output for wives, and I said, give me a written summary of this output, what am I looking for? What would you do? So recall what we had for wives. For wives, the outcome variable hard emotion in terms of the correlations, that is the effect of each variable ignoring the other predictors in the equation. Dyadic adjustment scale satisfaction was actually not significant. Trait attributions had a small correlation that was significant. And the event-dependent attributions had a moderate correlation that was significant. And then if we look at the question, what is the effect of each predictor after controlling for the others? Our results were that the trait attributions did have a significant standardized beta, and the other two, the two schematic variables, became non-significant. Satisfaction remained non-significant, and the trait attributions had a significant correlation, but they became non-significant after controlling for the other predictors. And then our overall R squared is 0.12, so we're explaining 12% of the variance in wives' anger. And we tested significance of that with our F test, and that was significant for wives. Although for wives, our p-values are not quite as small for husbands, and we have p-values that are not all rounding to 0.0000. Okay, so that's the wives output. Let's look at how we would give a written summary of these results. So here is a written summary. A lot of stuff there. Let's go through and see what we have. So the first sentence, I want to do a few things in my first sentence of this written summary. I want to, first of all, tell the reader that we're doing a multiple regression. So the reader knows what type of analysis we're talking about. We're not talking about, say, a difference between means. We're doing regression. So my very first words are in regression analysis, so that the reader knows we are doing multiple regression. Then, the other thing I want to do in this first sentence is I want to make sure the reader is aware of what the predictor variable is and what the predictor variables are and what the outcome variable is. So we've got 3 predictors, 1 outcome. What are the predictors and what is the outcome? So the outcome variable is wives' anger. And wives' anger during conflict was predicted using what? What 3 things? It was predicted using their event-dependent attributions, their trait attributions, and overall relationship satisfaction. So that sentence tells the reader, first, we're doing multiple regression, or we're doing regression. Second, it tells the reader what the outcome variable is, wives' anger. And then it tells the reader what our 3 predictors are, event-dependent attributions, trait attributions, and overall satisfaction. So now the reader knows what we're doing. At this point, we're going to, the remainder of our summary is going to go through those 3 types of questions we can address with multiple regression. We want to tell the reader about the results of all the variables taken together. We want to tell the reader about the results if you look at each predictor, ignoring the others. And we want to tell the reader about the results for each predictor after controlling for the others. So we want to address all 3 of those questions here. And let's start with the omnibus question. That is a general question of what is the percent of variance explained in the outcome variable using all the predictors taken together. That's a global question, kind of an omnibus overall question, a good place to start and the easiest place to start, so we will start there. And so in this example, we'll tell the reader what we found. We found that the 3 predictors explained a significant portion of variance in wives' anger. Now, of course, if that was non-significant, then you would say the 3 predictors failed to explain a significant portion of variance in wives' anger. In this case, it's significant, and most, if I give you examples on a test, oftentimes I'll be giving you things that are significant in that case. And so we say it was a significant percent of variance was explained. And then in parentheses, what I do is I give you those 5 pieces of information that we were just talking about, those 5 pieces of information that address the question of what is the total percent of variance explained in an outcome given all the predictors taken together. And so we want to go through that. What is the descriptive statistic that gives us an effect size? Well, our descriptive effect size is capital R squared, or multiple correlation squared. So R squared equals, what is the value? Our value was 0.12. And note that I'm going to round everything to 2 decimal places. So rounding to 2 decimal places, our R squared was 0.12. And then I put a comma right there. And then the next question is, what is the name of the inferential statistic that will test the significance of our capital R squared, or multiple correlation squared? Well, our F is the name of the inferential statistic. And when we talked about t-values and talked about giving written summaries of t-values, recall that I told you when you give written summaries, you write t, then in parentheses, you put the degrees of freedom for the t-value. We're going to do the exact same thing here, where we give an f, and then in parentheses, put the degrees of freedom for your f test. Now, one difference is with a t-test, we only had there was only one number that was a degrees of freedom. So you had a t, which was your with degrees of freedom. But with f, you have 2 different degrees of freedom. You have a degrees of freedom numerator and a degrees of freedom denominator. So if you go back, look at our table here. We've got here's our ANOVA table, and we have 3 degrees of freedom in our numerator. That's the number of predictors. We have 73 degrees of freedom in our denominator. That's our sample size minus number of predictors minus 1. Or our total degrees of freedom, which is n minus 1, minus our explained variance degrees of freedom, which is 3, gives us our error degrees of freedom, which is 73. So in writing my f value, I say f with 3 degrees of freedom in the numerator, comma, 73 degrees of freedom in the denominator. And when you're giving f values, it's just common APA style. Everyone knows you put f parentheses, and in those parentheses, the first number is your numerator degrees of freedom, a comma, the second number is your denominator degrees of freedom, and that's just the way we always do it. And you can also, if you read journal articles, then you should expect to see those degrees of freedom whenever you see an f value. And if it's degrees of freedom for a multiple regression, if it's a f value for multiple regression, you should be able to interpret and know that, okay, that first value is telling me how many predictors there are in the equation. And the second value is giving me an indicator of the sample size, or the sample size minus number of predictors minus 1, but I should be able to figure out the sample size from that second number. And you might want to look and make sure that your degrees of freedom match with your understanding of what the authors are doing in their analysis. Because sometimes you might be reading journal articles and you look at the degrees of freedom, and what you thought the authors were doing doesn't match the degrees of freedom that they're giving you. And at that point, you can realize something is not working right, or something you're not understanding. Oftentimes what that means is the authors did something they didn't tell you about. And if you're reviewing that article for a journal, that hopefully you can then write a comment there and say, well, you need to clarify what's going on here because your degrees of freedom don't match. If it's something already published, you're just kind of out of luck there. The authors did something that's not clear. It doesn't make sense. And I suppose that's a sign of maybe you might not want to put a whole lot of trust in that article if the authors are giving you degrees of freedom that don't match. So this is one thing that can make you a savvy, sophisticated interpreter of journal articles, is to be able to pay attention to degrees of freedom, understand what they mean, and make sure when you see degrees of freedom they match with what the article authors are telling you that they're doing in a study. So we've got f as our inferential statistic, degrees of freedom in parentheses, and then the f value, rounded to 2 decimal places, is 3.35. And then our p-value, I'm going to say p is equal to 0.02, and I'll follow this convention where I say if your p is greater than 0.01, rounded to 2 decimal places. If it's smaller than 0.01, then round to 3 decimal places. But if it's smaller than 0.001, then just say p is less than 0.001. And we've talked about that previously. Do the same thing here. And so our p-value is not less than 0.01, so I'm just going to round to 2 decimal places and say p is equal to 0.02. Okay, so that sentence we're just looking at here, the 3 predictors explain a significant portion of variance in wife's anger, and then I've given the 5 piece information, and that sentence addresses the question about what are the effects of all the predictors taken together. And now we're ready to look at the other 2 questions. What are the effects of the predictors ignoring the other variables, and what are the effects of each predictor after controlling for the other variables in the equation? And now, to address these questions, it's a little more complex because for the omnibus question, for the effects of all the predictors taken together, we have just one effect size. But for all these other questions, we have 3 predictors, so I'll have a separate answer for every predictor. So for the question of what are the effects of each predictor ignoring the others, well, we need to answer that 3 times, once for each predictor. The same thing for the question about what are the effects of each variable controlling for the other variables, we'll answer that 3 times, once for each predictor. And because we have a lot of information to convey there, at this point, it's going to be easy to make a table and put some of this information in a table. Part of APA style is if you do make a table, you always need to refer the reader to that table in your text. So what I'm going to do is I'm going to make a table, and I'm going to have a sentence here that refers the reader to my table. Correlations and standardized betas are reported in table 1, or whatever. It could be table 1, table 2, whatever number table it is. We'll call this table 1. Why don't we go ahead and shift to table 1 and see what I put there, and then we'll come back and see how I've summarized that table in my text, which is basically how we're going to do this. I put the actual numbers in the table, and the remainder of our text here will essentially summarize the information provided in this table. So let's look at the table. Here's how it looks. So I've got a title at the top. I've labeled it Table 1, and I give it a title to say it's predicting a wife's anger during marital conflict. And so give it some kind of title here. One thing about doing tables in APA style is that tables always are formatted in a particular way for APA style, and that they always have horizontal lines and never any vertical lines. And so I'm actually looking for tables to be formatted in this way, partly because I'm so used to seeing tables in APA style that if I see something different, it just stands out like a sore thumb. And if, for example, if I'm ever reviewing a journal article and someone submits an article and they have tables in there that aren't formatted with APA style, it stands out like someone's advertising, hey, I don't know APA style, I don't know what I'm doing, but I'm submitting this journal article. And right away, it gives an impression of someone being somewhat naive. And then I read the journal article thinking this person probably doesn't know what he or she's talking about. And the person's already off to a bad start. It gives a bad impression. So I want to save you from making bad impressions on people that are familiar with APA style. And for this class, whenever you give me a table, I want tables to be formatted using APA style. So for this type of table, we have one horizontal line at the top. Then we have titles, column titles or headings there. We have another horizontal line underneath that, and then a third horizontal line at the very bottom. So I've got 3 horizontal lines, no more, no less. Don't put lines here. And don't put never, ever put any vertical lines. Never do that. That's bad, bad, bad. Don't do that. That stands out like that is not APA formatted and looks bad for anyone who's used to seeing APA style. So 3 horizontal lines, no vertical lines. So we have one column here labeled correlation. We'll put our correlations there. One column for standardized betas. We'll put our standardized betas there. And here you just need to go to the output, see what those values are. I've rounded everything to 2 decimal places. So our correlations, negative 0.12 is this correlation between satisfaction and wives' anger. And by the way, note that in this I call this satisfaction, and I took away that DAS. In the output we were looking at, I called that DAS. And I called trait attributions was ATTRIBS, and event-dependent attributions was ATT1. But I don't use those cryptic names here because if I did, the reader wouldn't know what that means. Those are just kind of odd names. I needed to use those in my analysis because I needed to have short, quick names as handles to name all my variables to do my analysis. But when I'm giving the table here for a reader to look at this table and understand what I'm talking about, I never use those cryptic code names. I use normal English language to describe my variables. So I have the correlation between satisfaction and wife anger, correlation between trait attribution and event-dependent attribution there. So I have my 3 correlations, and then in my second column, I put my 3 standardized betas, 0.03, 0.06, and 0.32. Now, for significance and our inferential statistics, to try to put, we could try to put t-values and p-values in here. That would make this table be too much stuff. So we want a shorthand way to let the reader know what was significant and some general ballpark inequality of the p-values that we're working with here. So what I have is this note at the bottom says 1 asterisk. We'll put 1 asterisk next to anything where p is less than 0.05. 2 asterisks will be p is less than 0.01. And 3 asterisks will be p is less than 0.001. And I would like you to always use 1 asterisk to always mean p is less than 0.05. 2 asterisks will always mean p is less than 0.00 or 0.01. And 3 will always mean that p is less than 0.001. Because those are common ways of doing that. And if you do it differently, someone that's used to the usual way of doing it, might look at your table and not realize you're doing something that doesn't go with the tradition. So the tradition is 1 asterisk always means p is less than 0.05. 2 always means p is less than 0.01. 3 is p is always less than 0.001. And never use 1 asterisk for p is less than 0.01 or p is less than anything else. So 1 asterisk always means p is less than 0.05. Now, you can choose between a couple options here, and I don't care which way you do it. One option is to, every time you make a table, put all three options. Just always put 1 asterisk, 2 asterisks, 3 asterisks, and give the p-values for each of those. Put that at the bottom of every table you make. You could do it that way if you wanted to, or if you want to, you can just use the asterisks you need. For example, if we look up in this table, there's no spot where we actually use 2 asterisks. So if you wanted to, we could actually leave this out and just say 1 asterisk is p is less than 0.05, and 3 means p is less than 0.001. You could do it that way if you wanted to. So either way, you can always put all 3 or just use the ones you need, but always make sure that 1 asterisk always means p is less than 0.05 and so forth. So by looking at our asterisks, we can see that trait attributions was significant. We have an asterisk up here, so that means it was significant. We had just 1 asterisk, so we know that p was less than 0.05, but it was not less than 0.01. Event-dependent attributions, that has 3 asterisks, so we know that for that, p was less than 0.001, and that was significant. We have 1 asterisk over here for our standardized beta weight, and so we know that was significant as well. And then we have several values in our table where no asterisks, this correlation, these 2 standardized betas, there's no asterisks there, so we know that those were not significant. So that communicates to the reader what values were significant and which ones were not. So now we have our table here, and oftentimes it would be easiest to first create your table before you write your text that summarizes your table. So that's what we need to do next. We have our table. We need to go back to our paragraph and summarize the remainder of this paragraph. Will summarize what we have in that table. Now let's look at our table again here. Before we go to the paragraph, I want to call your attention to something here. And I've used this example because this example works pretty well because there's 3 particularly common scenarios you might encounter when you're doing a regression analysis like this. And I have all 3 of those possibilities in this example here. So note that what happened for satisfaction. For satisfaction, the correlation was not significant, and the beta weight was non-significant. And usually, if the correlation is not significant, the beta weight will be non-significant as well. Every now and then you have a situation where the correlation was not significant, but the beta weight became significant. And as you recall, what we call that's called a suppressor effect. That doesn't happen very often, but it might happen occasionally. What we have here, the correlation is not significant and the beta is not significant. So that's one scenario. Scenario number 2 is what we have for trait attributions, where the correlation is significant, but then in the multiple regression, after controlling for the other variables in the equation, that effect became non-significant. And then scenario number 3 is where, for event-dependent attributions, where both the correlation was significant and the standardized beta was significant. That is, after controlling for the other variables in the equation, we still have a significant effect. So we've got the 3 scenarios. One scenario is the correlation and the beta are not significant. Scenario number 2 is correlation significant, but beta weight becomes non-significant. Scenario number 3 is both the correlation and the beta weight are significant. And go back to our text here. This text essentially provides a template that you can use for each of those 3 scenarios. Now, one thing to keep in mind is that this text, this example, provides an example of each of those 3 scenarios, but in given an actual written summary of results, use only the parts of the template that you need. So if you have a situation where both the correlation and the beta are not significant, well, then use that part of the template that talks about that scenario. But if you don't have that, if you don't have a situation, if you don't have that scenario in your output where both the correlation and the beta weight are non-significant, then don't use that part of the scenario. So your task is to look at your output and identify, what do I have? And so given what I have, what are the scenarios I need to address? And then using the parts of the template that match what you need to do for your particular analysis. So I'm going to order this, start off by talking about the most important, the most the most amazing, the most outstanding, the thing that I get the most excited about. In other words, it's most exciting to have a situation where both the correlation and the standardized beta are significant. Everything's significant. We had a correlation that was significant, and after controlling for the other variables in the equation, it still remains significant. That's the most exciting thing. That's what we often really hope to have happen. So let's start there. So this first sentence is going to deal, or this section right here, I'll put it in a box. What I just put in a box here, this is the template you can use when you have a scenario where both the correlation and the beta weight are significant. So I'm going to start off talking about the correlation. There was a medium positive correlation between event-dependent attributions and anger. So medium is it's important. I'm telling you about the size. Is it small, medium, or large, or trivial? So I'm going to give the size, trivial, small, medium, large. In this case, it was a medium-sized correlation. And then I'm going to give the direction. Was it a positive correlation or a negative correlation? So those are two important things. Was the effect trivial, small, medium, large? What was the direction, positive or negative? So in this case, it was a medium positive correlation. And then I want to clarify medium positive correlation between what and what. What are the two variables I'm talking about here? It was between event-dependent attributions and anger. So this first half of the sentence summarized the results for the correlation. And it said, it told the reader, what's the size, trivial, small, medium, large, in this case medium. It told the reader what's the direction, positive or negative, in this case positive. And it told the reader what are the two variables involved, between a correlation between what and what, in this case between event-dependent attributions and anger. And note that because I'm saying there was a correlation, I'm implying that it was significant. I would not say that I had a correlation if it was not significant. So if I say I found a correlation, that's the same thing. It's synonymous with saying I found a significant correlation, because if the correlation is not significant, then you should not use the phrase there was a correlation. Only say there was a correlation if it was significant. And if you wanted to, you could say there was a significant medium positive correlation between event-dependent attributions and anger, but you don't need to say significant, because just the fact you're saying there was a correlation implies that it was significant. So that part of the phrase has told the reader about the correlation. Now let's go on and interpret the beta weight. And this first scenario is a situation where both the correlation and the beta weight was significant. And so in talking about the beta weight, I want you to show that you understand what it means to have a significant beta weight, that you understand that when the beta weight's significant, it tells you that these effects remain significant after controlling for the other variables in the equation. So I have that here. So event-dependent attributions explain unique variance in anger. So I say unique variance is that it helps the reader understand that this is explaining variance over and above the other variables. Explain unique variance in anger after controlling for the effects of the other variables in the equation. And that's important, that part. After controlling for the effects of other variables in the equation. That's an important phrase, because that clarifies, especially for this class, it clarifies to me that you understand what the standardized beta tells you. You understand that the standardized beta is giving you effects after controlling for everything else in the equation. So that is how to summarize that what I've got in the box right there. That is a template you can use whenever you have a scenario where the correlation is significant and the beta weight is significant. If you don't have that scenario, say you did an analysis and none of the beta weights were significant. Well, if that was the case, don't use this template. Only use that, what I have in the box, only use that if you have a significant correlation and a significant beta. Okay, let's go on to another scenario. The next scenario I'm going to look at, and I'm going in kind of a descending order from the most exciting to the least exciting. The second most exciting is where you had a significant correlation, but the effect became non-significant after controlling for the effects in the equation. That is, the beta weight was not significant. And I'm going to interpret the correlation the same way I interpreted the correlation for the first scenario, because both these scenarios we're looking at situations where we had a significant correlation. And when we have a significant correlation, I want to tell the reader about the size of the effect. Was it trivial, small, medium, or large? And the direction. Was it positive or negative? And I want to say there was a correlation, which implies it was significant, and tell the reader a correlation between what and what. So in this case, there was a small, that's the size, positive, that's the direction, correlation between what and what, between trait attributions and anger. So that's essentially the same template that we saw for the previous correlation, because both cases were summarizing a significant correlation. But at this point, this is where things get different, because this, what I have in this box, is the template for a situation where the correlation was significant, but the beta weight was not significant. That is, when you put everything together in the regression equation, the beta weight became non-significant. It was not significant after controlling for everything else in the equation. And I'm just going to say that. The effect became non-significant after controlling for other variables. So that just tells the reader that it became non-significant in the regression. One thing to note, just in terms of the language you use, is that in this example, I have 3 predictor variables. And so if a variable became non-significant after controlling for the other variables in the equation, if I have 3 predictor variables, then I'd use the plural after controlling for other variables, and I put the s there to make my variables plural, because I have a total of 3 variables, and I have the effects of 1 variable after controlling for 2 others. Do not put the s there if you have a situation where you're doing a regression with just 2 predictors. If I have just 2 predictors, you're getting the effects of 1 variable after controlling for the other variable. And it's simpler there just to name what that variable is, and certainly don't call that single variable variables with a plural s. So make sure you use the plural variables when you're talking about multiple variables, which will often be the case. But if there is a situation where you have just 1 predictor or 1 additional predictor, if you have 2 predictors and you're getting the effect of 1 after controlling for the other, just name what that other one is and don't use the plural variables. Okay, so that is what to do if you have a significant correlation, non-significant beta. Finally, what do you do if both the correlation and the beta are not significant? Well, that's pretty easy. Here I just say there was not a relationship. Or notably, you can write notably if you want to, or you don't have to write notably or whatever. But I have the key thing here is the relationship satisfaction was not significantly related to anger. And when I say it was not related, what I mean, it wasn't really due to correlation, beta weight, whatever I'm looking at, I didn't find any significant effects for relationship satisfaction. So I'm just saying relationship satisfaction was not significantly related to anger. And again, only use that if you need it. If you have a variable that had no significant correlations and no significant beta weights, then use that template. If you don't have that scenario in your output, then don't use that template. Every year I get some people giving me written summaries where they don't quite figure that out and get rather confusing things where they say things like, in this analysis, all the variables had significant correlations and all the variables explained unique variance in the outcome after controlling for the other variables. And none of the variables explain unique variance after controlling for the other variables, and all the variables were significant and none of the variables were significant. And I'm thinking, that makes no sense whatsoever. You've just contradicted yourself 3 times, and it is clear you do not know what you're talking about. So don't do that. Don't say nonsensical things. Make sure you use the template that fits the analysis you're working with. Okay, let me just summarize a few of the points in given written summaries. So 1, in reporting results, all numbers with decimals are rounded to 2 decimal places. And the one exception would be p-values. We've talked about that before. If your p-value is smaller than 0.01, round it to 3 decimal places. Or if it's smaller than 0.001, then just say p is less than 0.001. I've talked about formatting the table. The table has only 3, no more, no less, 3 horizontal lines. The table has no vertical lines. It has 3 horizontal lines, no vertical lines. You've used asterisks to indicate p-values in the table. 1 asterisk, 1 asterisk means p is less than 0.05. You have a title at the top of your table, and your table has a note at the bottom explaining what the asterisks mean. And in addition to these notes, there are a couple other things to note about given written summaries to multiple regression analysis. The first is to not be redundant. This particular example, I had 3 different predictors, and every predictor had a different scenario. One predictor had a significant correlation and a significant beta. Another one had a significant correlation, but a non-significant beta. And then the third had a correlation and a beta that were both non-significant. But what if you do analysis and you have 3 predictors and all 3 have significant correlations and all 3 have significant betas? What would you do then? Note that I have this template here. This sentence here, there was a medium positive correlation between event-dependent attributions and anger, and event-dependent attributions explain unique variance in anger after controlling for the effects of other variables in the equation. Kind of a long sentence there. What would it be like if you took that sentence and clicked and pasted it 3 times and just changed the name of the variable every time? Well, that would be kind of long and lengthy, and that would make for terrible reading. If you were reading that, you'd guess this is like dry and boring. It's like, why did you just paste this thing 3 times and you're making the reader read the same thing over and over again? So don't do that. If you have output that allows you to condense what you're saying and say it more concisely, then do so. So for example, if you had 3 variables, say you had 3 predictors, and all 3 had significant correlations, and all 3 had significant betas, you might say something like, in this analysis, variable A, variable B, and variable C all had medium positive correlations with the outcome variable, and they all explained unique variance in the outcome variable after controlling for the effects of each other. So that's one way you might do that. Or maybe variable A and B had medium correlations, but variable C had a large correlation. So you might say, variable A and B had medium positive correlations with the outcome variable. Variable C had a large positive correlation with the outcome variable. And all 3 variables explained unique variance in the outcome variable after controlling for the effects of each other. So those are a few ways that you might condense your text. The important thing is don't just click and paste the same sentence over and over and just change the name of the variables. Don't do that redundant type of writing. When you can, be concise. Another thing to mention here is what do you do if you have a suppressor effect? We haven't looked at that type of example here because that's kind of rare. It doesn't happen that often. But what if that happened? What if you had a situation where your correlation was not significant, but your beta weight was significant? What do you do then? That's what we would call a suppressor effect. And in that case, you can just simply summarize it similar to what we have here, but you would just say, although the correlation between variable A and the outcome was not significant, there was a suppressor effect, and this variable explained unique variance in the outcome after controlling for the effects of the other variables in the equation. So you could just summarize a suppressor effect that way. And that is everything for how to give written summaries of regression. We've been talking about regression with just a single step. I have one more example that will involve regression with multiple steps, and we will go to that in just a moment.